Assalamu alaikum warahmatullah. So today's objective is here the power. Okay, how we define the power in physics. It's our today's I mean concern to discuss. But before that, it's very important to mention something like in a way in a system energy is not of course usually remain constant with time. I mean we can add or remove energy from the system always with respect to some rate. Okay, when we talk about the car. Okay, if we take an example of car, for instance, if the car it accelerates, means that we add some energy to its mechanical energy. Okay, and when we apply brakes to the car, means that there is some kinetic energy that turns into the heat. Okay, and all that. So under this perception, we come to the conclusion we always we always give some rate at which we can remove or add energy from the system. Okay. So by that way, it becomes very important for us when we discuss this term. Okay, it has good applications indeed also. So how we define this power term? Basically, we define it under the domain of physics, like it's a rate of doing work. Rate of doing work. Okay, rate of doing work, or I can say the releasing energy into a system, the rate at which energy is being released into a system, and that's indeed the definition of power also. So how can give the mathematical shape to this statement here? Like I use here the term rate of doing work. Okay, so if I will just come to this kind of conclusion here, when we talk about if I will just remind my definition of work done for a lateral displacement, it will be yes f dx. Okay, f dx. Okay, so this is something that we know at the very basics of the discussion of this unit and all that here. So if I will do here some further maths in a way like so if this is my force here, and I can divide it by dt element here and multiply it also by the dt. It does not make any remarkable difference here. It seems one are the same, but if I will put this dt here, okay, so it will be my yes f of dx by dt, that's something like v. Okay, so the rate of doing work, it is something known as power. Okay, so power is basically defined as the dot product of force and velocity. Okay, or I can say fv, the cosine of angle, where theta here is an angle between the force and the velocity vector. Okay, if there is my force vector in this direction and there is my velocity vector in this direction, and the angle we have between these two vectors, and when we define the dot product, it's nothing but the power. Okay, power again here, it is something called as a scalar parameter. Okay, so because here if I look to the mathematical way, and it's a dot product, and dot product is also known as a scalar product, because when we solve the dot product, we will get at the end a scalar parameter. So by that way, this dot product takes care of everything. In a way, we can easily say that our power, it is a scalar quantity. Okay, it is a scalar parameter. Okay, so this is how we define the power in the language of physics and all that. It is something the rate of doing work. Okay, that's what we call as the power. So if I will just do here the simple problem on this context, what's that basically? If I will just mention here the problem which is based on the power equation, the power expression I got, it is something like the dot product of the force and the velocity. Okay, so here if I will just mention my problem, in a problem if it's given like we have I can say here is my if this is my rocket here. Okay, and the rocket, it delivers the constant thrust that pushes the rocket up. Okay, if the engine of the rocket, okay, in a model of rocket, and its engine delivers a constant thrust that pushes the rocket up. Okay, if I'm assuming that the mass of rocket is almost constant, means that when the rocket engine of the rocket pushes, this delivers the kind of thrust and it pushes up the rocket for a constant. If mass of the rocket is going to remain constant for a given time, let it be t. Okay, if there is a thrust delivered by the engine of the rocket that is responsible for pushing it up, okay, for some time, if its mass is going to be, remain constant, and I can say here, there is not, so much smoke. If mass is, approximately constant here for this time interval t. Okay, so I can say that my smoke is not going to be shoot off more rapidly by the rocket for this time. Okay, and if I want to know how exactly the power will be delivered by the engine of rocket for this time, how I can calculate it? If it's also given in a problem like the mass of the rocket is m. Okay, so as you know, rocket, it's a well-known example of what I can say, the variable mass problem here. But if I look to the content from the question, like the rocket engine, it basically delivers the constant thrust, okay, which is responsible for pushing it up for a given time interval, and we assume that this mass of the rocket, it remains constant, means that before it can shoot off the smoke. Okay, so mass, it will be constant, although when we talk about the rocket problem, it's a typical variable mass problem, as you know. But here the story is somehow different for this time interval. If we have the kind of thrust delivered by the engine of rocket, which is responsible for pushing it up, and here is a mass that remains constant for this time interval, I can just look to, from this kind of step, before it can make it the kind of, before it shoots off, I have the constant mass here. It is something that looks more logical to to think in a problem in this way and all that. But if I look to the if I will just analyze my problem here in the gravity field here, look. So if mass of rocket is m in a gravity field, it will have, I will just come across, as you might have known, in the rocket problem we got the kind of expression like this. Okay, this is something which is very familiar to us, and it's a kind of in Newton's second law, which we use here. It's a thrust and it's a weight. It's a net force which provides the kind of net acceleration in an upward direction. Okay, so in order to calculate the power here, the force, thrust is given here. I have no need to calculate it. But how I can calculate velocity? I can calculate velocity from here. If I look to this equation, my acceleration will be 1 over m f minus mg. Okay. Now, if I will just calculate my velocity here, that dv by dt will be equal to 1 over m f minus mg. Okay. If I will do here the one more step, my v will be equal to simply 1. M is constant, f is constant for a given time interval. So here it will be, after integrating, it will be t plus c, where c is some constant of integration, but we can remove this constant of integration here. Why so? Because rocket, it starts from rest at t is equal to 0. Rocket is at rest, rocket velocity is 0 here. Okay, obviously at velocity at t is equal to 0, that's 0, means that I can drop this constant of integration here, c. Okay, because initial velocity of the rocket is here 0, so it will be v at some time t, it will be 1 over m. Okay, f minus mg. Hope you are getting it. This is my velocity for a given time interval t. For that my mass of the rocket remains constant for this given time interval. By this way, I can look for the given power expression and I can calculate the rocket power here. the power I will get after introducing this equation, after switching this equation, I can call that equation more safely. That's a power, rocket power. Okay. So here, if I look to this equation, first of all, how I can solve this dot product here. Look. If this is my upward thrust here, and this is my velocity here. Okay. So as you know, the rocket velocity we are talking about, it's a relative velocity, but here before it shoots up, I have simply the velocity here. So it will be obviously this force and the velocity, they are in the same direction. Okay. So my power will be simply yes Fv. Hope you are getting it. This is an upward thrust. Okay. So more generically, when we talk about the relative velocity of this rocket with respect to the smoke, that has an upward direction, that is an upward moment. Okay. So basically, if I look it that way, and also I can safely look to this dot product, it will be simply come Fv, because F is in the direction of velocity. Okay. So here I got my power expression like this. Thrust is given, I have no need to calculate it, but if I will just switch the value of velocity here, it will be yes, 1 over m F minus mg, yes, here is t. Okay, here is t. This is a time interval for which thrust is constant here. It will be yes, 1 by m f square minus mg f t. Okay, this is I can say the rocket power. I can say the rocket power according to given information and all that. Okay. Rocket power. Okay. So this was all about how we can calculate, we can use the this power equation somewhere under more different physical intuition and all that. This was about this. So my next video, it will be on collisions. Okay. So take care. Okay. So wait for my next video. It will be totally based on the good kind of concepts. That's good kind of discussion. That's what I can say, the collision theory. Okay. So